So today I want to discuss issues related to the temporal statistics of earthquakes and the recurrence interval, and specifically try to relate them to underlying fault properties and to heterogeneity on faults. So of course, when we talk about the periodicity of faults and the temporal statistics, one of the first quantities that comes to mind is the recurrence interval. So the recurrence interval is very fundamental to the way we think about seismic hazard. You know, even in the media, when you read something about the San Andreas fault being long overdue, the statement implies an assumption of periodicity or quasi-periodicity of some sort, and the idea that there is an underlying recurrence interval that we can somehow estimate. And so the questions I want to address is whether this assumption is justified and also what controls the recurrence interval. So specifically for the recurrence interval, I will start from very simple cases related to small repeating earthquakes and then think about how heterogeneity, including roughness or the presence of damage, can affect the recurrence interval of major earthquakes. So before we do that, let's take a step back and think about the statistics of earthquakes in a broader sense. So what we see if we look at a regional catalog, it's nothing like a quasi-periodic sequence with a predictable recurrence interval. Instead, we see a combination of Poissonian background activity, and overlaid on that, we have strong temporal clustering, which is basically dominated by aftershock sequences. And this can be seen in the statistical distribution in the probability density function of normalized inter-event times, where basically these two types of behavior give rise to either a power law distribution in inter-event times due to aftershock decay, or this decaying exponential, which represents Poissonian background. And this distribution can also be derived theoretically. It's shown here by the gray line, which is basically a combination of the two. And it is seen in basically every regional catalog that you look at worldwide, as you can see from this data. So one aspect that I want to focus on is how can we understand this underlying distribution, but also think about some of the exceptions to this, and specifically repeating earthquakes. Repeating earthquakes are only a small fraction of the events we see in a catalog, but they tend to be quite periodic. And so they have the advantage of having a well-defined recurrence interval. So they're a very good candidate to understand what controls the recurrence interval. And finally, another family of earthquakes that we can find sometimes in catalogs, even though they are by no means pervasive, are foreshocks. And the temporal evolution of foreshocks is also debated. If you stack many catalogs, you find that foreshocks tend to accelerate according to this 1/t dependence, where t is the time to the main shock. However, if you look at individual catalogs, you don't typically see this acceleration. You see more, swarm type behavior, or sometimes you see main shock aftershock sequences, but you don't necessarily see a clear acceleration. And so we would like to understand if physically, if there are reasons to expect such an acceleration, or if it is an artifact. So overall, the overarching question is what controls the recurrence interval and earthquake statistics. And from a physical point of view, the easiest way to estimate recurrence intervals is to think about a cycle of a spring slider loaded at a constant rate or a constant shear stressing rate. And if earthquakes have a constant stress drop, then the recurrence interval is just given by the ratio of the stress drop to the loading rate. And the approach I will take is basically to think about heterogeneity of each of these individual quantities separately, and then trying to understand how this heterogeneity gives rise to specific patterns on the fault and how it controls the recurrence interval. So an example of heterogeneity due to loading is basically any fault which is loaded by a creep on the side of the fault or surrounding the fault or down deep of the fault will have heterogeneity in that we have much faster loading near the creeping region. For example, in the down deep section of the seismogenic zone of a vertical strike slip fault, or for an asperity, we have higher loading rates near the creeping fault. We also expect heterogeneous loading rate from all sorts of other processes. So this is an example, a figure from a paper by Xi and Barbeau, where they're showing viscoelastic relaxation. And we also expect that something like viscoelastic behavior will have some spatial patterns. And I will not discuss them here, but it's just another example of how loading will create gradients in the background stress. If we think about other sources of loading, including stress changes from nearby earthquakes, or volcanic activity, we also expect all of those to have some spatial gradients. We also expect heterogeneity in fault strength. This is more of like an intrinsic property. If we think about the stress drop as the product of a change in friction coefficient multiplied by the normal stress, then we expect any variation in these two to reflect in a variation of stress drop. For example, normal stress varies with depth. We also expect variations of normal stress if there is excess in the variations in pore fluid pressure. So we may have regions with a lower normal stress, for example. We also expect variations in the frictional parameters, for example, long wavelength variations due to temperature dependence, which is going to give variations in the stability and A minus B, but also perhaps more local variations due to different rock types, so that we might have kind of this alternation of velocity weakening and velocity strengthening in a small fault area. And finally, we also expect some heterogeneity due to geometry. And particularly here, I'm showing heterogeneity due to normal stress variations due to roughness. So we have a rough fault here shown in black, and we have this normal stress heterogeneity, which is basically a consequence of the roughness itself. And this is a very local type of heterogeneity that we will expect will take place everywhere. So the overlying argument is that if we understand this heterogeneity either in loading or in strength, we can then derive the temporal statistics, including earthquake clustering, and we can also say something about the mainshock recurrence interval. The problem may seem intractable, given that heterogeneity is almost by definition quite complex, and we have all these different sources. But I will show that we can combine numerical simulations and fracture mechanics to basically tease apart different types of heterogeneity, and in some cases really quantitatively understand how heterogeneity then reflects in earthquake statistics or the recurrence interval. So I'm going to begin with small repeating earthquakes simply because they are simple. They are the simple type of cycle that we see in nature. And as I said earlier, they have a well-defined recurrence interval. So we would like to understand this because it's a very first order feature. So small repeating earthquakes, we tend to think of them as occurring on seismic asperities loaded by creep. And if we use the argument outlined earlier, where we take the recurrence interval to be the ratio of the stress drop to the loading rate, then we can take the loading rate on average is inversely proportional to the dimension of an asperity. And now, assuming constant stress drop, we can relate this to the seismic moment, which gives this expected scaling where the recurrence interval scales with the cubic root of the seismic moment. However, this is not what is seen in the data. In the data, we see a scaling which is also power law, but the exponent is not 1/3, it's 1/6. And I argue that the problem with this derivation is that we are using an average loading rate. And again, the loading rate is heterogeneous. So we have velocity strengthening behavior and velocity weakening asperity. So we expect the loading rate to be higher at the edge, and then basically induce some creep within the asperity at the boundary. And then as the stress level increases, this creep front will shrink. And then eventually this will lead to nucleation. And so I suggest that this is a more physical way of thinking about the recurrence interval for this heterogeneous loading. And in practice, in order to estimate this propagation of the creep front, we use fracture mechanics arguments, which are based on essentially energy balance. The idea is that the stress field in front of the crack tip is controlled by both stress changes within the crack itself. I'm using crack basically as a synonym for seismic rupture in this context. And the stress field is also controlled by loading, which in this case will be heterogeneous. And both of these sources of stress can give rise to a stress concentration, which tends to favor propagation of rupture. However, the stress concentration may only allow rupture to propagate if it exceeds a critical value. This critical value is known as fracture toughness, and it is related to the fracture energy, which is required to create a new crack surface. So a condition for crack propagation, which we can now derive thinking about heterogeneous loading or heterogeneous stress drops, is that the sum of these two terms has to be at least equal to the toughness for a rupture to propagate. For a rupture to propagate, or I should also say, or for creep to propagate, because in this case, you're specifically thinking about penetration of creep within the asperity. So this approach allows us to calculate an equation of motion, which is shown here. So this tells us how fast the creep front propagates towards the asperity. And then we can basically ask when the next earthquake will nucleate by requiring that the creep front either reaches the front of the asperity or that it propagates a sufficiently far distance, which is related to the nucleation length for this asperity. And if we do that, we obtain this analytical expression shown here by the blue line. And first of all, we see that the analytical expression is a very good fit to the results from simulations shown here in black. And secondly, we see that the analytical expression predicts the scaling with the power of 1/6. So this is just a short example to demonstrate that by thinking about heterogeneity in loading, we can get a much better sense for the recurrence interval of events on a small asperity. However, as I mentioned earlier, these asperities are the exception. These really small repeating earthquakes with very periodic behavior, they are the exception and not the rule. So we also want to understand rupture arrest. And rupture arrest specifically because it will give us a more complex temporal pattern and a more complex frequency magnitude distribution. So the idea now is that in addition to having a criterion for earthquake nucleation, we also want to derive a criterion for rupture arrest. And this is also derived from fracture mechanics, basically in the same way I outlined earlier. And so we are basically asking how often do earthquakes that nucleate, in this case, loaded from below, how often can they reach the opposite end of an asperity? And here for computational simplicity, basically we run simulations in 2 dimensions. We look at an anti-plane fault loaded from below so that we can explore a broader range of fault dimensions. And the main result from this work is that we can predict the number of earthquakes per cycle. And we find that the ratio of the number of partial ruptures to the number of full ruptures is proportional to the square root of the dimension of the fault divided by the nucleation dimension. And this is true for rate and state friction with the aging law, but in the paper, I also present expressions that are applicable to more general types of friction. In this figure, I show that the theoretical expression shown by the dotted line is a good fit to what we see in the simulations shown in gray. And in terms of temporal statistics, we find that when we only have full ruptures, we basically have these very, very periodic events. On larger asperities, we start seeing this bimodal behavior. We have some smaller and larger events, and they have a bimodal recurrence pattern. And we see much more complex behavior with clustering and the loss of periodicity for faults that exceeds the nucleation length by a few hundred times. We can look at this by looking at the interevent time distribution. So here this is shown by the blue line. And we basically find that in the simulations, we reproduce the same interevent time distribution, which is found in nature. So we have this power law distribution for small interevent times, which is mostly controlled by aftershocks driven by afterslip in the creeping section of the fault. And then we have this more Poisson-like behavior. We don't get exactly Poissonian behavior. There is still a little bit of periodicity, but overall, these large faults are much less periodic than the small ones. So this was just an overview of how we can think about heterogeneity in loading rate and how by including this heterogeneity, we can reproduce the recurrence interval of smaller earthquakes. And we can also reproduce the statistics of a single fault that is much larger than the nucleation dimension. And we find that the statistics is very similar to regional statistics. And then in the second part of the fault, I want to focus on heterogeneity, not in loading, but instead heterogeneity in fault strength, and specifically due to fault roughness. So we chose fault roughness because this is a very first order source of heterogeneity. We know that faults are fractal across many orders of magnitude. And so we run simulations with rate and state friction, and these are 2D plane strain, fully elastic simulations with a fractal profile with a Hurst exponent of 0.7. And in this case, the fault is approximately loaded at a uniform rate. So we're taking away the source of heterogeneity that we considered before. This is an example of what an earthquake cycle looks like. We're looking at slip on a log scale as a function of position and as a function of time to the main shock. And we see a very abundant foreshock activity. We have a foreshock sequence and creep occurring at the same time. There is another video that you can check if you want more details on the Foreshock sequence itself, or you can check out our paper from 2021. I will only summarize one result that is specifically related to the temporal statistics of foreshocks. What we find when we stack several catalogs is that we have a 1/t acceleration in seismicity rate. We demonstrated that this can be explained by thinking about the interaction between creep patches and locked asperities, which I will describe later in the talk. But on top of this 1/t acceleration, we also see strong examples of temporal clustering. So if you look at a single catalog, you may not be able to see this 1/t acceleration because individual catalogs may be dominated by this stronger clustering and mainshock aftershock sequences. Now, I want to take a step back, and now instead of thinking about the foreshocks, I want to describe everything that happens leading up to the foreshock. So what happens during the interseismic phase on this heterogeneous fault? What we see here on the right is that the interseismic velocity is much higher on a rough fault on average than it is on a flat fault. And on this figure, you can see that this is basically due to the occurrence of localized creep, alternating locked patches. So I want to highlight that this is conceptually quite similar to the creep that we saw in the case of heterogeneous loading. Essentially, in the previous case, we had much higher stresses around the asperity, and so those regions started creeping first. Whereas in this case, we have regions of lower strength, and in the next few slides, I will show that that is the case. And so regions of lower strength also reach failure sooner, and they can start creeping. And in both cases, the creep itself is very subtle. It's much slower than what we typically think of as a creeping fault. It's the order of 10 to the minus 10 meters per second or 10 to the minus 11 meters per second. And so this is probably not something that could be seen geodetically. However, it plays a very important role in determining when earthquakes nucleate. So even though this creep is very localized and very minor, we really need to include it if we want to understand the seismic cycle as a whole and its duration. So as I said, the heterogeneity in geometry, roughness, basically induces heterogeneity in normal stress. We have locations with higher normal stress and locations with lower normal stress. And it is the combination of these two that gives rise to these alternating creeping patches and locked patches. Essentially, low normal stresses are related to the creeping patches because these regions have a lower stress drop, and they reach failure sooner in the cycle. They tend then to creep at a stable rate because the low normal stress tends to make them stable. So if we want to understand the cycle, we basically want to understand how these creeping patches evolve and how they expand in time. So from this figure, you can see that the creeping patches indeed correlate with the low normal stresses, and we want to understand what controls their temporal evolution. So we can do this by thinking about a heterogeneous stress drop, and now thinking about shear stress from tectonic loading increasing at a uniform rate as shown here. However, we also have an additional component to loading. Basically, as soon as creep begins, these creeping patches are now loading the locked asperities. So the total shear stressing rate now is the sum of the tectonic component plus a component which is due to redistribution of stresses from creeping into locked patches. We can estimate the steady state sliding velocity on the creeping patches, which is a function of their size, so that the creeping patches actually accelerate as they expand. And we can now also estimate this component of additional loading rate. So in this figure, I'm showing some analytical results that you can see in the dotted lines that are obtained from this simple idea of redistributing stresses from creeping into locked patches. And you can see that they are quite a good fit to all the simulations, except for one case where we have very little heterogeneity. So this is not a valid framework, but otherwise, we can basically understand the progression of the cycle by considering this expansion of creeping patches and how they load the nearby asperities. So the redistribution of stresses from creeping patching into asperities can basically explain why the recurrence interval of faults with roughness is much shorter than the recurrence interval of planar faults. As you can see in this figure, when we are looking at the rough fault, the recurrence interval is almost a factor of 2 smaller than the case for the planar fault. And so basically this explains why we have more frequent main shocks once we have roughness. Now, I will spend the last few minutes adding one more component of heterogeneity by considering also the effect of damage around the main fault. I will show that damage is also very important in determining the state of stress on the main fault and also in determining the duration of the seismic cycle. And damage here is expressed explicitly by including segments that basically have the same frictional properties as the main fault itself. In this figure, we are looking at the seismic cycle of a simulation without any damage on a rough fault. And below, we're looking at the seismic cycle on the same fault, but with damage around it. And we are only looking at slip velocities on the main fault. So these are main shocks. You can see that once we include damage, the duration of the seismic cycle further decreases. And to understand this, we need to see what happens on a secondary fault and on the main fault throughout the seismic cycle. So just like before, after a main shock, we see this very subtle localized creep on the main fault, and we have these locked asperities. If you look at the secondary fault, you see the creep is much, much more vigorous. We have higher sliding velocities and we have much larger patches, and you see that the creep actually accelerates during the main shock itself, and these patches expand. This was very surprising at first, simply because the stress change due to the main shock is negative everywhere in its vicinity. So you expect that after the main shock, the main fault will have a lower Coulomb stress overall, and it will be further from failure and will tend to be quiescent. But this is also true for all these subsidiary faults in the near field. So you would expect them to be quiescent as well. But we see that this is due to the state of stress on the main shock fault right after the main shock is quite different from the state of stress on subsidiary faults. So on the main fault, we're looking at the state of stress before the main shock in blue and the state of stress after the main shock in yellow. As you expect, the fault is brought further from failure on average. We have a decrease in shear stress, but you can also see that the state of stress at the end of the main shock is basically controlled by dynamic friction, because all the fault is participating in the earthquake. The strength is just given by the dynamic friction coefficient multiplied by the local normal stress, and this is always in equilibrium with the shear stress. This needs not be the case on any fault which has not slipped during the earthquake, because it doesn't have to be at the dynamic friction coefficient. So on a subsidiary fault, we see basically the same exact average change in shear and normal stress, but we see that while many points are brought much further from failure, there are some points that are brought closer to failure or even above failure. And these are the points where we see this accelerated creep during the main shock. So now the secondary fault is creeping much more vigorously than the main fault during the interseismic phase. And this is also true for all the other faults in the vicinity of the main shock. And so they are more ready to generate events, to generate foreshocks specifically. And another secondary fault generates an earthquake that then leads to this acceleration. And now we see basically this aseismic acceleration leading up to the main shock. It's now not happening on the main fault, it's happening on a secondary fault, and it's happening earlier than it would have otherwise, because the secondary fault can experience creep even very, very early in the cycle. And so once again, we see that understanding how creep evolves right after a main shock and throughout the seismic cycle is really key to understanding how long it takes for this major fault to nucleate the next main shock. So to summarize, I've shown that heterogeneity in either loading rate or in strength can explain several characteristics of seismicity, both in terms of its statistics and in terms of the recurrence interval of large events. In terms of temporal statistics, we see that when we have heterogeneous loading by a down deep creep, we can basically reproduce the interval time distribution seen in regional catalogs, even though we're looking at a single fault. So we don't really need any complexity in the fault properties, that the gradients in loading are actually enough to give rise to quite a complex statistics. We also see that if you add heterogeneity due to geometry, including damage or roughness, we tend to see this accelerating Foreshock sequence with a 1/t acceleration. Oh, sorry. And finally, we find that heterogeneous loading can explain the recurrence interval that we see on individual asperities surrounded by creep, and it's a much better to the observations than if we were considering the average loading rate. And then finally, that geometrical heterogeneity produces shorter recurrence intervals, basically by loading the seismogenic parts of the fault, these locked asperities, by loading them faster because creep can take place elsewhere where the strength is lower. And so as an overall conclusion, I would say that this localized creep, which is due to heterogeneity in either a stress state through loading or in strength, for example, through geometry, really have a key impact in the seismic cycle of the fault as a whole, even though, as I said, it's very localized creep at a very low velocities, but it seems to control the duration of the seismic cycle overall. And thank you. I will now take a couple of questions if we have time.